back of your soda bottle, see if you have some high fructose corn syrup or perhaps a little soybean oil in your cookie, you're probably dealing with these crops. But honestly, I'm a little bit of an unlikely speaker on this topic. The crops that I just talked about would fit in what I would call these global, large, specialized, machine-driven, centralized kind of agriculture. I personally spend most of my time working over in this area here. I work with diversified fresh market vegetable crops, vegetable growers. I'm the one that can probably tell you what pesticide was sprayed on any of your vegetable crops and why they were managed that way. That's the world where I spend most of my life in. And, but I got interested in these crops as they were first coming about, which was, well, the first commercial release was 1996. We're in year 17, 18. We're closing in on 2 decades of this. And I got interested in them as they were, in the early 90s, mostly because I was working with small-scale diversified vegetable growers, and pesticides were being applied, insecticides were being applied, still are. And I was interested in farm worker safety. So I was thinking, well, perhaps this host-plant resistant trait, if you will, might influence insecticide loads, insecticide management, and how's that going to influence pest management. Most of these crops are not in vegetable systems right now. Here's an example where they showed up in vegetable systems in 1996, right when they got started in potatoes. BT, Bacillus thuringiensis, I'll talk about that later, was moved into transgenic potatoes, mostly for russet potatoes, for cultivars that were most relevant to the far northwest. And you can see it started, adoption rates were moving up in an exponential pattern. This is still just maybe 2% of the acreage, but it was moving up in this pattern like occurred in all the other things, and then bang, stopped sale altogether. Just because this technology is developed and has some potential for some reasons, it doesn't mean it's going to go out there in the marketplace. In this particular case, what happened was the BT potato was moving up in the adoption rate. Most of the cultivars that it was relevant to at the time were moved into processing potatoes, French fries, chips, things like that, which means that the marketing channel is fairly constricted. All you need is Frito-Lay, McDonald's, Burger King, a half a dozen processors would say, well, I don't know if I want to deal with that crop. I have market risk. And if you put a BT potato out there, it was designed to control the Colorado potato beetle. I'll just pick on Frito-Lay, I don't know if it was them per se, just any of these processors. Why does Frito-Lay care whether you use an insecticide to control Colorado potato beetle or a BT potato when you open yourself up for market risk? Some kind of demonstration, people saying, well, we're not going to support you for this. So that constriction in the marketplace said, we're not going to buy those potatoes, and within a year, the people that were manufacturing said, forget it, we're out of here. It brings up an interesting question. I'll show you later what, in the case of sweet corn, we saw something similar where we had a fairly rapid rise and then a dramatic drop, but it didn't drop to zero for all kinds of reasons I don't have time to go into here. But the places where it stayed related to places where marketing channels were more diversified, essentially fresh market people who are selling direct retail. And there it's creeping back up again. So, I asked the question, who chooses the cultivar? Here they've taken, they're doing some, it was, you don't see a lot of this anymore, but 10 years ago you would still see a lot of hand harvest sweet corn for the wholesale packers that are moving their stuff up from Florida, Georgia into, I'm sure, this part of the world for a couple months. They top the corn, and they top the corn to make it easier for the harvesters to work in it. And there are these guys picking it and throwing it in the conveyor belts. They call them mule trains. And, you think any of those folks had any choice in what cultivar was chosen? Who's going to choose the cultivar? We have BT sweet corn cultivars right now that in South Florida can drop insecticide loads, number of applications from 17 to about 3. Are they going to be adopted? Should we label? What would we label it as? This was an example where I actually tried it. I tried labeling it and putting it in grocery stores, 6 different grocery stores throughout Philadelphia. Watched how consumers responded, and we can return to that. But this is a big issue right now. There's at least some 15 or 20 states where this is being proposed and working its way up and down various regulatory debates and votes, etc. Should we label? What should the label say? Is it an information label that's going to help people have a right to know and give you information about what you're really dealing with in an agricultural system? Or is it a brand that's basically serving to say, like it, don't like it, whatever kind of thing is on a marketing brand? We can return to that. What I want to make you realize quickly is that the GMOs that I talked about, I showed you 4, there's about a half a dozen, we're really in our infancy on what could happen. And you can go to this website, and I hope I can pull this up. This is a website in the U.S. They have similar websites throughout the world. They're public. If you want to take a GMO crop and start working with it and studying it, perhaps for commercial development, but at any point where you want to say, I want to do a field test, I want to put this out in a field setting, you need a permit. In order to get the permit, you have to go to, in the United States, you have to go to APHIS, the Animal Plant Health Inspection Service. It's a branch of the USDA. So let's, we can search these permits. Here's permits for, I'll go and make it simple, different kinds. So you can search by organism, institution, phenotype, all these different things. We'll just search by organism now. And I'll just submit a request. This is live. And hopefully, no results. Go back. Make sure we're live here. So if we search by organism, oh, okay, this is working. I got it live. So here we are. I hope you can see that. Here's the organisms that you would come up. I mentioned cotton, soybean, canola, corn. What about alfalfa, Bahia grass, banana? I'm not familiar with the, okay. Black nightshade, blueberry, camellia. You get an idea of all the different kinds of options that people have done field tests on, and we're not. Let's see if I can get that. Okay. So let's pick rice. And there's no transgenic rice on any kind of market right now. But here's page 1 of all different institutions, etc., and where people have done field tests on transgenic rice. And you see a bunch of them are fairly recent, and we're on page, this is page 1 out of 7. We're in our infancy on what we could do with GMO technology and what people have looked at. Let's see, so now I go to the PowerPoint, right here. And slideshow. And okay, so that's the only, you can go to that website yourself and see what people have looked at. And you can also pick the phenotype. What is it that they were looking for rice to do? And I'll just start focusing on insect-resistant transgenes. So the first ones that we really came up with that are out there now are things that confer resistance to viruses that are transmitted by aphids. So we have, aphids as piercing, sucking insects. We have a complex of viruses that some have very complicated biological symbiotic relationships, but we have a bunch that are to put it simply, if I was talking to growers, I say just pretend you're dealing with flying hypodermic syringes. You know, the aphid comes in, pierces, pulls up virions in the sap, it attaches to some proteins very selectively, and the very next time that aphid feeds, the very first thing it does is ingest fluid into the plant, and bingo, you know, you've got the virus moving. So you get these flying hypodermic syringes. They're very hard to manage when they're in a system. Even insecticides, you end up, if you have to use insecticides, you end up having a lot of problems because you can't kill the aphids fast enough. You'll get a lot of situations, and I've seen this, where you don't have any aphids that you can find, but the virus is all over the field. You killed the aphids, but the virus has moved on quicker than you can kill them. So here's examples of papaya being killed by papaya ring spot virus, and here's commercial transgenic fields of things that are stopping this from happening through RNAi technology. And this now, something, last time I read about this, they said 75% of the papayas coming from Hawaii are using this kind of technology. So that's one example. Another, that same kind of technology has moved into a number of different cultivars of squashes, zucchinis, but it hasn't moved beyond that. There's a wide range of cucurbit crops that are susceptible to watermelon mosaic virus, zucchini yellow mosaic virus, cucumber mosaic virus, papaya ring spot virus, but we're not seeing this moved on further. The one that you folks probably hear the most about is Bacillus thuringiensis, BT, I think, right? You've heard of BT corn? Frankenfood corn? No?
No.
So Bacillus thuringiensis is a common soil bacterium. And it was described around 1920, somewhere in 1930, 1940, it was developed into insecticide. Bacillus thuringiensis is probably the most common insecticide that's used by certified organic growers. There's dozens of formulations, and the formulations, when you spray them, you'll have some bacterial cells here. You'll have these crystals. You see this right here is a crystal. They call it formed from the cry gene. It expresses these cry proteins, capital cries for the proteins. And you also get spores. When the bacterium is grown up in fermentation culture, as it starts depleting its nutrients, it'll sporulate. And it'll make these spores and it'll make these crystals. If these crystals get ingested by usually lepidopterans, caterpillars, it's the most common case. I'll show you a range of cases next, but most common cases, certain families of caterpillars, when they ingest this, the crystal protein breaks up into 4 major subunits. In order for that to happen, the gut of the lepidopteran has to have a pH of about 11 or 12. It's very, very basic. You know, our pH is 3, 4, 3. So, I mean, we couldn't possibly do this. We would digest this like you would a protein. But if it breaks up into the subunits attach to specific receptors on the insect gut lining. That causes some pores to open, and you get mortality coming from septicemia as the gut contents and the hemolymph interact, or just from osmotic pressure. So it's a fairly specific interaction between certain insects and certain BT proteins. So we've got these BT proteins. You also have vegetative insecticidal proteins that are not visible here because they're soluble. When you spray this in certified organic systems, you will get a mix of all of this, and you have to be a little bit careful because there has been a few cases where the bacteria germinate in the eye and you have some problems in your eye. But what happened around, well, in the 80s and now is commercialized, is the genes that make these crystals have been pulled out, manipulated so that they can be expressed by the plant, inserted into the plant, and you get the plant expressing these protein crystals. So now the caterpillar feeds on this, and it kills them. You can do it with a lot less dose because you've got very good ingestion occurring with a neonate, with a first instar caterpillar. And that's BT corn. Just to make sure you realize that this is the most common thing, BT corn. But the proteins from BT, we now have at least 250 insecticidal proteins. There's all kinds of phylogenetic trees trying to identify them. I just want you to realize that they're kind of in families, if you will, phylogenetic families. So there's the crystal 1 family, the crystal 3 family, and they target different species. They target different life stages of different species, and so you can get these different BT plants, but they're dealing with very specific cry proteins and cry genes. And today, when you work with transgenic plants, you've got these vector stacks and pyramids. So what I'm referring to here, in this case, this is an example that, this would be a Monsanto example, where the plant is expressing the Cry1A.105, which is very effective against European corn borers, and it's also expressing the Cry2A, which is effective against these species here, which is in a different insect family. You get a little activity of this, you get a little activity going this way. Then you also have the Cry3s, which is active against these beetles, and you've got this gene here, which is giving you herbicide tolerance. The fact that you've got more than one cry protein aiming at more than one target makes this part a pyramid. The fact that we have different species targeted, in this case beetles, in this case weeds, then we call it a stack. So you get these stacked pyramid products that are out there in agriculture today. And when I'm interacting with growers, I have to explain, what are you buying and why, and how do you manage that? And just to give you a couple quick more examples before I move on, this shows you an example of this would be the isoline, the sweet corn cultivar that everything else in this picture is bred from, and an example of the kind of damage we were getting. This is the kind of damage with the Cry1A. This is the kind of damage with the stack product that's just coming out now. It gets complicated. And the other thing that gets complicated is we're not only dealing with transgenic tools in agriculture, but most of our larger scale agriculture are coupling a lot of other things with the seed as well. Other technologies that are not GMOs at all, not transgenic technologies, but they come from technologies that are aimed to help preserve the seed in storage and shipping, which have now moved into systemics, things that move up through the plant, which include insecticidal properties, fungicidal properties, plant regulator properties, inert ingredients that are not truly biologically inert. Some of these are things that you find in the cosmetics that you'd use on your hands, or hand lotions, or things that are being used to help get penetration and dispersion across a membrane like you would for a medicine. And these technologies are being moved into agriculture to protect plants. There's thermoregulators involved. So these are non-GMO technologies that are getting coupled in with GMO technologies. So agriculture is getting complicated. We're also seeing, I mentioned the RNA for the aphid-transmitted viruses. We're also seeing RNAi. I expect in 2 years, we'll see this aimed at some beetle larvae as well. And we're also seeing people use different